Okay, we're recording. All right, so good morning, everybody. Welcome back to Math 115. I hope everybody had a restful 3-day weekend. Yesterday was President's Day, so what did I do? I just kind of hung out. I got my sleep schedule all messed up, so I'm really tired now. Maybe some of you guys can feel that too. Anyways, I suppose I'll start by sharing the screen. And today I want to start by going back a little bit because there's one aspect of the rational function graphing which I feel like I could have explained better or more clearly. So I've kind of rewritten this section of the notes to try to communicate that more effectively. So let me just remind us first what the setup of what we were talking about was. So we were talking about rational functions, so functions of the form n of x divided by d of x, where n and d are polynomials. And we were trying to figure out how to graph these things. So we kind of talked about horizontal asymptotes, vertical asymptotes, and holes. Those were kind of the big things. Okay, and a vertical asymptote was when the function was really kind of blowing up, like how we see in the graph of 1 over x. It's getting really, really huge when x is kind of close to 0. Okay, and it happens to be that 1 over x gets really, really huge on the right side of 0, and on the left side of 0, it goes down to negative infinity. Okay, and we kind of introduced this limit notation where we say that the limit as x approaches a from the right. In this particular example, our a value was 0, so we would write the limit as x approaches 0 from the right of f of x would be infinity, and the limit as x approaches 0 from the left of f of x would be negative infinity. And when I first defined these vertical asymptotes, all I really said was that these are going to commonly occur at x values where we have d of x is equal to 0 and n of x, okay, the numerator is not equal to 0. Okay, so the denominator is 0, but the numerator is not 0. Okay, at those values, we're usually going to have a vertical asymptote. And what I feel like I could have explained better is how to determine what this kind of blow up behavior looks like for various different situations where we have the denominator 0 and the numerator not 0. Okay, so that's what I'm about to talk about. Let me scroll back down to where I was talking about that. Okay, so I'll go a little bit slower this time. We were just considering a function f of x. Okay, so f of x is a rational function. Okay, so it's a polynomial divided by a polynomial. And what I've written here is that the numerator is just being left as is on top, but I've factored the denominator. Okay, the denominator here has been factored a little bit. Okay, I took this power of x minus a to the power m out. Okay, so I'm assuming that x minus a to the power m is a factor of d of x. In other words, if I were to plug a into the entire thing of d of x, it would be 0. Okay? And here, q of x is what I get when I do the division of d of x divided by x minus a to the power m. Okay, if I were to do this in long division, then I would get q of x. Okay, so all I've done in the denominator is just sort of factored out this term, x minus a to the power m. Okay, and my assumptions here are that I have factored out as many possible terms of x minus a to the power m as possible, okay? So the point is that q of a is not equal to 0. In other words, there's not like another x minus a hiding somewhere in this q of x, okay? We've gotten them all out, okay? That's the point there. And then, of course, we want our numerator to not be equal to 0, because otherwise then we would have a hole. Okay, so we say that the numerator is not 0, and the denominator is split into the part that will be 0 and the part that's not 0. Okay, so once we have that, then what we're going to do is the following. We're going to look at the sign of n of a divided by q of a. Remember, these are both not 0. So this number in this box here will have a sign. It will either be positive or negative, right? All numbers which are not 0 are either positive or negative. Okay, so depending on the sign of this number, okay, which is basically just what's going on with everything that's not the factor. Okay, so we just look at everything that's not the factor and we look at the sign of that thing. And we also look at the multiplicity m of the 0, okay? So depending on if m is going to be even or odd, okay, then we're going to wind up all told with 4 different possible behaviors, okay? So we choose a as either even or odd, or excuse me, a is either positive or negative, and m should be either even or odd, okay? And that leaves us with 4 possible situations, okay? So I've split them into this table here to kind of describe what's going to happen. Okay, so you can always refer back to this table, like when you're doing your homework or something. Okay, and this table is kind of meant to just tell you immediately what's going to happen, and then in a second I'm going to explain why these things happen, okay? So if m is odd, then we break into 2 possible situations, okay? Either a is positive or a is negative, and if a is positive, we get this blow-up behavior that looks like 1 over x, kind of. And if a is less than 0, we get behavior which this looks kind of like, I don't know, maybe f of x equals, why don't I not put a function on there? It'd be like x minus a negative 1 over x minus a, something like that. Okay, so if a is negative and m is odd, then the behavior here is going to sort of reverse. Okay, see how this kind of reverses? We have blow up behavior on the left side, and then we have blowing up to negative infinity on the right side. Okay, so that's the difference between those two. And then when m is even, okay, we're actually going to wind up with the same behavior on both sides of the asymptote. They're either going to both blow up to positive infinity or both blow up to negative infinity. Okay? And it's easy to remember which one is going to happen. If a is a positive number, then we blow up to positive infinity. And if a is a negative number, then we blow up to negative infinity. Okay? So this is the reference table, and I'll spend a second explaining why this stuff happens because I feel like maybe I could have done a better job of that last time. So let's just take this first scenario, okay? We're going to take m is odd and a is larger than 0, okay? So we're going to have this kind of green behavior here. And let me explain why that happens. Okay, and I could even add something in here, which might make things even a little bit clearer. Okay, so limit as x goes to a from the left of f of x is going to be equal to, remember our f of x is n of a, x. So it's going to be n of a divided by q of a times x minus a to the power m. Okay. And so depending on the sign of n of a and q of a, we're going to write that number as just a. Okay. And then we're going to consider what is the sign of this number. And then ultimately, our goal here is to determine whether we should have a negative sign on this infinity. We know we're going to blow up to some kind of infinity, and we want to know, should it be negative? Okay. And all we want to do is consider what is the sign of this entire fraction here. And if we know what is the sign of the numerator, if we know the numerator is positive or negative, then we can figure out what the sign of the denominator is, and then we'll be pretty much done. We'll have the sign of the entire fraction. Because we know if we divide a positive by a positive, we'll have a positive. If we divide a positive by a negative, we'll have a negative, and so on and so forth. Okay, so I just check. I see that x is going to a from the left. Okay, so x here is going to be a number which is slightly less than a. So if I take a number which is slightly less than a and I subtract a from it, I'm going to get what I wrote here is a small negative number. Okay, so ultimately I'm dividing a, which is a positive number, by a small negative number. And that's why my blow-up goes to minus infinity. So I know when x is approaching a from the left, okay, things should be going really far down, which is why when I do this in green, I'm going to draw this thing going way down like this. Okay, so this is the sort of pseudo proof as to why this is happening. Okay. And likewise, if a is going to be less than 0, okay, then when I eventually get to the end here, I know that a is going to be a positive number. And when x is approaching a from the right, I know that x here is going to be a number which is slightly bigger than a. If I subtract something which is smaller than my original number, I wind up with a positive number. So I do a positive number divided by a positive number, which is very small, and I get something going to infinity. Okay, which is why on the right side of this thing, wrong green, on the right side of this thing, I'm going to be going up like that. Okay. So I don't want anybody to be confused in particular about what this A thing is. You know, it kind of seems like I pulled A out of thin air, but it's not pulled out of thin air. It's just the name that I give for the number n of a divided by q of a. Okay. Okay, can I get some feedback? Does this make a little bit more sense now that I've kind of slowed this down and explained this a bit further? Okay, is anybody still quite confused about why this behavior is happening? It's okay if you are. I need to know so that I can dig a little deeper on this. Okay. Then I'm going to keep going here. So that's the basic process that we do for all of them. Okay, the next one I'm going to go through a little bit faster. Basically, we see, okay, yeah, basically, okay, we see now we have a is less than 0, okay, and m is still odd. Okay, so we're going to replace this whole thing, except here this time a is going to be a small negative number, or just a negative number. a will be negative. And we divide a negative number by a small negative number, and we get a positive number, which is very large. Likewise, again, here, a is going to be negative. Okay? And since we're doing the same thing, we're going x to the a to the left, and x goes to a from the right. Okay? M is still odd here, so nothing in the denominator has changed from case 1 to case 2. The only thing that's changed is that the numerator here, a, switched from being positive to negative, which is why instead of going to negative infinity, we went to positive infinity, and instead of going to positive infinity, we went to negative infinity. So if I were to draw this, I know that since when the limit as x approaches a from the left goes to positive infinity, then when I go from the left, I'm going to go up. And I know that the limit as x goes to a from the right. Okay, so as I'm approaching along the x-axis in this direction, getting very close to a from the right, I know that I should be going down to negative infinity. Okay? And as you can see, this is just like I said, it's kind of the reverse of the other one, right? We're going down when we were going up, and we're going up when we were going down. It's just because of the sign change of this a here. Okay, and the only really interesting thing here about cases 3 and 4 is the following. When x goes to a from the left, then x is some number which is slightly less than a. So this whole thing will be negative and small. But when we take a negative number to an even power, we actually get a positive number. Okay? Negative number to an even power, we get a positive number. So in this case, we're actually going to see that these two terms here, x minus a to the power m and x minus a to the power m, depending on whether x is slightly less or slightly larger than a, they're going to give us actually the same sign of number here. Okay, we're going to get a small positive number in both cases because the power is even. Okay, and since we know that a is positive throughout this whole thing, we know that a here has the same sign in both of these things, and we know that the denominator has the same sign in both of these things, so we should expect the end behavior of both sides to be the same. Okay, they're both going to positive infinity because we divide a positive number by a small positive number, we get something which is very large and positive. So therefore we get this. And then finally, the only thing that changes from case 3 to case 4 is just this sign change on a. We now say that a is less than 0, but we still have a positive number in the denominator on both of these two things because of this even power m here is going to just make that denominator positive no matter what. Okay? Except now we know that a is negative. So we take a negative number, divide it by a small positive number, we get a negative number which is really large. And again, this one's negative. Okay, so we get both of these guys going down. Okay, so that is behavior of rational functions near a vertical asymptote. We get one of these 4 behaviors, and it depends basically on the multiplicity of the 0 in the denominator and the sign of, I guess, what I would call the leftovers, right? The parts of the rational function which are not the 0 in the denominator. Okay. Any questions about all of this stuff? Okay, I think I have one example here, which I feel like it would be reasonable to go through. So we're going to do it. As they say, a stitch in time saves 9. I don't know, maybe only old people say that. But I'm going to say it today. Okay, so we want to graph this function here. Okay, I suppose it is a function, so we better write f of x is equal to this thing. And it's rational, so we know we have to basically consider 3 things. We need to consider the possibility that there are holes, we need to consider what's happening with a horizontal asymptote, and we need to consider what's happening with a vertical asymptote, or vertical asymptotes. Okay? So, in fact, let me just move this, I'm just going to move this whole graph down to the second page here. And I'm going to first go through each of these things. So, I don't know, let's start with horizontal asymptotes. Well, remember what happened with horizontal asymptotes was we wanted to look at the degree of numerator and denominator. Okay? And remember, we said that if the power of the denominator was larger than the power of the numerator, then our horizontal asymptote was going to be 0. If the power of the numerator is larger than the power in the denominator, then we don't have an asymptote. And if the power or the degree of the polynomial in the numerator is the same as the degree of the polynomial in the denominator, then the horizontal asymptote will be the ratio of the leading coefficients. That's what we said about horizontal asymptotes. Now I can see in this case, the bottom is degree 3, and the top is degree 1. Right? The largest power of x in the numerator is 1. And if I were to FOIL out the denominator, then the largest power of x in the denominator would be 3. So since the degree is larger in the denominator, I know that when x becomes really large, the denominator is going to outweigh the numerator. So I know that the horizontal asymptote, so let me write it out. Denominator has larger degree. That's telling us our horizontal asymptote is y equals 0. Okay, so we got our horizontal asymptote. And remember, horizontal asymptotes are just dealing with what's going to happen when x becomes really large. Okay, so second, let's check for holes. That's places where n of x, that's values a, I guess, where n of a is equal to q of a, or not q, but d. d of a is equal to 0. Okay, the numerator and the denominator are both 0. So let's check. Are there any values which we could plug into the numerator which will make it 0? Yeah, sure, we could plug in 1. If we plug in 1, then the numerator will be 0. If we plug in 1 to the denominator, we'd get 1 squared times 2. So the denominator is not going to be 0 when the numerator is 0. Okay, so we're not going to have any situations here where the numerator and the denominator are both 0, because the numerator will only be 0 if x is equal to 1. And when that happens, the denominator will be something else other than 0. Okay, so no holes. Okay. We don't have any common factors, basically, between the numerator and the denominator. Okay, and finally, we check vertical asymptotes. Which, remember, that's when n of x is not equal to 0, but d of x is equal to 0. And there's two places where that's going to happen. Okay. That's going to happen if x is equal to 0, because we have this factor x squared. And it's going to happen when x is equal to -1. So let's categorize them. We've got x equals 0 and x equals -1. Now, what I want to do for each of these is figure out what is a and multiplicity of m. Okay, so I want to fill something in this green blank here. Should be a greater than sign or a less than sign. And I want to fill in something in this green blank here. It should be the word even or odd. And then I'll have my handy table to tell me what the picture is going to look like. Okay, so let's start with x equals 0 here. What do we think is the multiplicity of x equals 0 in the denominator? We're just looking at the multiplicity of the 0, x equals 0 in the denominator. What do we think? No takers? Okay, let me just remind you, the multiplicity of a 0 is going to express the power, the number of powers of that factor, which we can factor out. Okay. So first of all, the corresponding factor for x equals 0 being a 0, the factor is just x, right? And as we can see here, in the denominator of our function, we factored out x squared. So what is the multiplicity of this 0? Yeah, it's just 2, right? The multiplicity of the 0 is, in this case, is 2, right? You can think of this as being like x minus 0 to the power 2, right? But we don't need to write x minus 0 because x minus 0 is just x, right? Okay, so the multiplicity of this 0 is 2. So is the multiplicity even or odd? Yeah, it's going to be even here. Okay, now let's worry about figuring out what a is. Remember, a was defined to be the value of basically the leftovers other than our 0. So we're going to look at x minus 1 divided by x plus 1. And what we're going to do is we're going to plug in the value that would make this 0, 0. So we're going to take 0 and plug it into x minus 1 over x plus 1. So a is going to be 0 minus 1 divided by 0 plus 1 equal to -1. And that's less than 0. So I know that I should have a less than sign here. So I have a less than 0 and m is even. And that picture looks like our purple one. It's going to look like this, basically. Okay. It's going to be going down to negative infinity. Okay, now let's try the other one. Let's try x is equal to -1. What is the multiplicity of the 0 x equals -1 in the denominator? Yes, Sam, I can. Okay, before I ask that question, let me answer Sam's question. So is, how did I know that the multiplicity of this 0, x equals 0, was even? Well, I'm looking at the 0, x equals 0. I know that this corresponds to the factor x. So I go up to the denominator, and I look at this thing, and I check, here's the factor x, and I want to know what is its multiplicity. Its multiplicity is the power here on our factor. Since 2 is an even number, I call this multiplicity 2 is even. That's how I did that part. Does that make sense, Sam? Okay. So what's the multiplicity of the other 0? X equals to -1 has multiplicity what? Yeah, it should be odd, and the multiplicity of it is just 1, right? We only have 1 power of this factor. Okay, so for the other one, we know that m is going to be odd. It's just 1, right? And now I want to check about a. Remember, a is going to be what we get if we plug -1 into what I would call the leftovers, okay, the stuff besides the 0. We know if we plug into the 0, the denominator is just going to be 0, and that's boring. So we just want to check what happens when we plug x equals -1 into the other guys. So I'm going to do -1 minus 1 on the top. And then the denominator will be -1 squared. So I get -2 on top, and in the denominator I get 1. So I have a is less than 0, and m is odd. Okay. And that's going to be our, I think it's our blue behavior, where we're going down. No, that's not right. We're going up on the left side and down on the right side. Okay, so all I'm going to do now is kind of stitch this together. All right. The first thing I'm going to recognize is that my horizontal asymptotes means that very far out, okay, I'm going to look something like this. It's going to get very close to 0. Okay, then I know that I have a horizontal asymptote at x equals -1. And I know it should look like this picture here at x equals -1. We should be going up to the left, and we should be going down from the right. So I'm going to draw that like that. Okay, and then our next thing, we should have also a horizontal or a vertical asymptote at x equals 0, right? That was the other vertical asymptote that I had. So let me draw that in. Here's x equals 0. And I know that the behavior of the graph near this vertical asymptote x equals 0 should be that it's going way down to -infinity on both sides. So I should be going way down to negative infinity on both sides, so I know it should look something like this on both sides. Okay. And now I'm just going to kind of like fill in the gaps, basically. It looks like the way we would fill in this thing is just by connecting this into like a U shape or an N shape, I guess. And then it looks like the way we would fill in this gap over here is by, like, I don't know, just connecting those. Okay. And actually, I can do a little bit better, because I know that the numerator is 0 when x is equal to 1. So it should look something like this. Okay, so that's how we would draw a graph like this. We basically just check the behavior near these vertical asymptotes and fill in a bit of the graph nearby, and then we just kind of like try to connect the remaining pieces with a smooth curve. Okay, I think that's the end of what we're going to talk about, graphing rational functions. So what do people think about this graphing rational function stuff? Does this feel better? Does it feel good? Does it feel okay? You think you could do it on your own? Maybe. Okay. Well, there'll be a homework assignment on this stuff that hopefully once you get some practice with this, it'll be more clear. Okay, but this is kind of an important skill to have. Knowing what these functions look like can be quite useful. Okay. And we're gonna move on if there's no other, comments or questions about this stuff. I know there's kind of a lot to consider when you're gonna graph one of these things, but just go through one by one, check the horizontal asymptotes, check the holes, check the vertical asymptotes, determine the behavior near these asymptotes, and then just try to like fill in as much information as you can on the graph and then just connect the rest of the pieces. You know, this is by no means a perfect graph. I'm sure the graph of this thing looks slightly different. But we've got probably most of the key features of the graph on our picture, okay? And that's what we're looking for. Okay. So we're going to move on now, talk about something else. I'm sure I've put you all through enough hell graphing rational functions. So instead, we're going to talk about polynomial and rational inequalities, okay? And in particular, really, graphing rational functions is one way in which you can check rational inequalities. But I'm going to show you another way in case you really don't like graphing rational inequalities, which I get the sense that some of you don't like doing that. So let's start by just talking about how we handle a polynomial inequality. Okay, so a polynomial inequality is something like this, where we have an inequality with a polynomial on both sides. Okay, we have a polynomial on both sides of an inequality. So a greater than sign, a less than sign, greater than or equal to sign, or a less than or equal to sign. Okay, and here's how we're going to solve it. The very first step is to get everything onto one side. Okay, just move everything over. In fact, why don't I just go ahead and go through these steps one by one. Okay, so the first step is just get everything over to one side. So we do x cubed plus 3x squared minus 9x plus 5 is greater than 0. And now we're going to do sort of what we've already done with some other inequalities. Basically, what we're going to do is we're going to list the zeros on a number line, and then we're going to pick a test point from each interval between zeros, and we're going to check whether the inequality is true in each interval, and then we'll write our answer down using either inequality notation or interval notation, okay? And then finally, we have to consider the possibility of whether this thing is a greater than sign or a greater than or equal to sign or a less than sign or a less than or equal to sign. Those are going to tell us whether we get brackets or parentheses on our interval notation. Likewise, it's going to tell us whether we get open dots or closed dots on our number line. Okay, so that's kind of where we're going here. But the first step is to just get everything on one side. And then the second step is to list all of the zeros on a number line. Okay, so let me ask a slightly harder question, but I'd like somebody to respond if they don't mind. And just ask, how can I find... So the question is the following. How can I find all the zeros? I guess we don't need an E on zeros, do we? All the zeros of a cubic polynomial. Did we learn any way that we could do that? We know how to find the zeros of a quadratic polynomial, right? We could use the quadratic formula, or we could factor. What about a cubic one? Here I have something of degree 3. How do I handle something like that? Just stick an x outside. Okay, well, we could definitely do that as long as every term had an x, but we wouldn't be able to pull an x out of this 5 here. But you're right, GCF would be a fantastic option if I had everything except for this 5 here. Then I could do that, and then I could just factor the remaining quadratic function, which would be inside. That would be a great idea. But this 5 here is going to really kind of mess us up with that. Does anybody remember what we learned about before we learned rational functions, what we were doing? Yeah, take a common factor, but that's the problem. That's what I'm kind of asking is how do I find out what the factors are? How do I factor a cubic polynomial, right? That is really the question. And I'll give you a hint, it has to do with long division. Is this turning gears for anybody? Okay, seems like not. That's okay. I'll answer my own question here. The answer is we want to do this long division ultimately. Okay. So we want to set up something like x cubed plus 3x squared minus 9x plus 5. Yeah, Sam's got it. And what we want to do is put something out here, something like x minus something, blank. And we want it to be a factor of what's inside our division sign here, so that when we do the division, everything comes out very nicely and we wind up with remainder 0. So I want to just guess a factor. And what that means I should do is I should guess numbers to see if anything is going to make this 0. Okay, if I plug into x cubed plus 3x squared minus 9x plus 5, I want to check, is there anything I can plug into that such that I'm going to get 0? Oh, 3. That's going to be hard to guess. I don't think 3 is going to work. 3 we'd get like, what, 27 plus 27 minus 27 plus 5. So these two would cancel out and we'd wind up with 32. So 3 is not going to work, but we could try some other numbers. Yeah, I think positive 1 is going to be a good one. If we plugged positive 1, what would we get? We would get x cubed would be just 1, right? We get 1 plus 3 times 1 minus 9 times 1 plus 5. And if we do this subtraction, we'd get 1 plus 3 is 4, minus 9 is negative 5, plus 5 is equal to 0. So I think positive 1 is going to be a 0. Okay. So since x equals 1 is a 0, that means x minus 1 is a factor. So the answer was guess a factor, basically. Then do long division. Okay. So we guessed a factor, and that's great because we only really need to guess 1, because after we do this long division, we're going to wind up with a quadratic. Okay. So I'm going to do x minus 1 here, and I'm going to do long division on this guy. So great, our old friend is back. We get to do some long division. We love that. So remember, what should go here should be the number which I get when I divide the leading coefficient, or the leading term of our dividend by the leading term of our divisor. So that should be x squared. And then what I should go ahead and do is I should multiply x squared times our divisor here and subtract underneath the division sign. So I subtract parentheses x cubed minus x squared. Okay, the x cubes cancel. That's how I chose x squared, was so that those would cancel. And then I'm left with 3x squared. I should add x squared because minus negative x squared I should add. So I get 4x squared minus 9x plus 5 left over. And now the next term of our quotient should be whatever I have to multiply x by in order to get 4x squared. Or whatever I get if I divide 4x squared by x. Okay. So now all I'm going to do is subtract, and I'm going to get 4x squared minus 4x. I cancel these guys. That was very much by design. And then I get negative 9x plus 4x is going to be 5x, negative 5x plus 5. And so the last thing that I should put in my quotient is going to be whatever I get if I divide negative 5x by x, and that's negative 5. Okay? So after I do minus 5, I get minus negative 5x plus 5. And the result is everything cancels. and we're happy. So what have I done? I've reduced the problem to x minus 1 times the quotient of this thing, x squared plus 4x minus 5 should be greater than 0. Okay, and now all I have left to do to figure out where the zeros of this thing are is check what are the zeros of this thing. I can factor it, right? So I get x minus 1, and I factor that dude. It looks like we get an x plus 5. And an x minus 1. Did I do something wrong with my long division here? I may have done something wrong. Minus 9x plus 5. No, it seems like this worked out. Hang on. Let me make sure I didn't make any mistakes here. So I did x squared. I got minus x cubed minus x squared, so I added the x squared, and I got 4x squared minus 9x plus 5, and then I did subtract, where I did 4x. So negative 9 minus negative 4x is negative 5x plus 5, and all I had to do was subtract 5 and get this. Okay, cool. And then finally, this does factor as x plus 5 and x minus 1. So okay, we get a double root. No problem. So here's what I'm going to do now. Now that I have all of these things being multiplied together, all I'm going to do is plot them on a number line. Okay, and I guess the only places that I really have to plot are going to be at -1. Excuse me, at -5 and +1. Hang on a second. Something is killing me about this long division process. I feel like I better double check this and make sure that I'm not doing something wrong here. Plus 3x squared minus 9x plus 5. Okay, no, I did everything right. Okay, sweet. So we get just these two zeros, all right? So we've got x minus 1 with multiplicity 2, and then we have x minus 5, or x plus 5 with multiplicity 1. And all we're going to do now is pick a test point from each interval, and we're going to plug it into the function and see what we get. Okay, so I'm going to pick the test points, maybe -6, and I'll pick the test point 0 in the middle. That's usually an easy one to plug in. And then I'll pick the test point 2, okay, from the final interval. And now I'm just going to plug. And I'm just going to plug them into our function, which is neatly factored. So I'll try -6 minus 1 is going to be -7. So x equals -6 gives us -7 times -6 plus 5 would be -1. And then ultimately, we're going to get -7 again for the third factor. We multiply all these things together. A negative times a negative times a negative is a negative, and this will all be less than 0. And that doesn't jive with what we're supposed to be getting, larger than 0. So this interval is a bust. Now let's try x equals positive 1. Why don't I just do it to the right? X equals 1. Well, we would get 1 minus 1. Sorry, what am I doing? I need to be trying x equals 0. Okay, next 0. So we would get 0 minus 1 times 0 plus 5 times 0 minus 1 is equal to negative 1 squared times 5 is equal to 5, which is larger than 0. So this interval here is going to be good. So let's recap where we're at. We have no good here. This region here is doing what we want it to do. It's giving us something positive. Now we just have to check the last region here. So finally, we try x is equal to positive 2. And we plug in, we get 2 minus 1 times 2 plus 5 times 2 minus 1. And we get 1 times 5 times 1 is equal to 5, which is, again, larger than 0. So this region is going to be good. Okay? So we've plugged our test points. And now the last thing we really need to determine is whether or not we should include our actual zeros. Okay, but remember the zeros, the things that make this left-hand side 0, we would get then 0 is larger than 0, which is not true. So we're going to have open dots. Okay, so if I were going to actually draw this using, I don't know, how about green? I would do it in the following way. We'd have an open dot on 1. We'd have squigglies in between 1 and 5. We'd have an open dot on 5. And then we would have squigglies to the right of 1 as well. So my final answer would be x is in the interval -5, 1 with parentheses, union 1, infinity. Okay? So that's how we do these polynomial inequalities. So let's recap. First, we get everything on one side and factor completely. That took some work for us because we had to do long division, but we got there. And the second step was to list the zeros on the number line. Okay, so we took all of our zeros and we just put them on a number line. The third step was to pick a test point from each interval and check whether or not we get a true statement when we plug it in. If we do, then we fill in that entire subinterval. And if we don't, then we don't fill in that entire subinterval. And then the last step is to check the endpoints, or I guess the points where we actually get 0. Since our inequality was a strict inequality, we did not include the points that caused the left-hand side to actually be equal to 0, because then we would get a statement which is not true, because 0 is not larger than 0. It's equal to 0. Okay, so that's how we do polynomial inequalities, okay? It's pretty easy when we have a quadratic because we can just go ahead and factor the quadratic or use the quadratic formula. It becomes slightly more complicated when we have a polynomial of higher order. If we have a polynomial of higher degree, then we need to try guessing a factor and then dividing it out using long division, okay? So if I were going to try this problem and I really just had no clue what is going to make this thing 0, I would try numbers like -3, -2, 1, 0, or -1, 0, +1, 2, and 3. Just try those numbers, and if none of those make that thing 0, then, well, I would be shocked if there was like an exam question and that none of those were a factor. That would be highly irregular. In fact, I'm telling you that I'm not going to do that. Okay. Any questions about solving polynomial inequalities? Okay. Seems like not. In fact, we've already seen this sort of test point technique when we solved rational inequalities, which we did back in the inequality section. But we're going to talk about it again here. Okay, we're going to talk about it again. And I guess there's really a slight difference here, which is we're going to consider things like this, where we might have a rational expression on both sides of the inequality, okay? So we've already talked about how to do inequalities where we have like, I don't know, x minus 1 times x plus 2 divided by x is larger than or equal to 0. We already talked about how to do inequalities when we have just a rational expression on the left side and 0 on the right side. Okay, but we're going to kind of expand our understanding and also consider the possibility that we have a rational expression on both sides. Okay, and the process is going to be basically the exact same as the polynomial inequality, except for a couple of things. First of all, we are going to get everything on one side again, and then this is the new part. We're also going to write it as a single fraction, okay? So we're going to move everything to one side, get a common denominator, and write everything as a single fraction. Once we have it as a single fraction, again, like before, we're going to factor completely, numerator and the denominator this time. And then we're going to plot the zeros of the numerator and the denominator on the number line. And then we're going to pick a test point from each interval. And then we're going to figure out whether we should have closed dots or open dots on the points which are actually 0, depending on whether or not we have a greater than or equal to sign, a greater than sign, or a less than sign, or a less than or equal to sign. Okay? And there is one thing that I have to consider, which is the following. When we get our common denominator on the left-hand side, the zeros of the denominator are always going to get an open dot no matter what. Even if we have a greater than or equal to sign or a less than or equal to sign, we're still going to put an open dot on anything which is going to cause the denominator to be 0 because that's not actually in the domain of the expression. So I think really the best way to show these is just to solve them out here and follow these steps and get a little extra practice here. So that's what we're going to do. So let's take our steps one by one. The first step, I should take everything to one side. So I get 2 over x minus 1 minus 1 over x minus 2 is larger than or equal to 0. Now I need to write the left-hand side as a single fraction. So I need to find a common denominator. So what I'm going to do is I'm going to take the denominator, which is x minus 1, and I'm going to multiply x minus 1 on the bottom and on the top of this one. And on the other one, I'm going to take the other denominator, x minus 2, and multiply by that on the top and on the bottom. So what do I get? In the end, I'll have x 2x minus 4 minus x plus 1 divided by x minus 1 times x minus 2 is larger than or equal to 0. And I can rewrite that numerator. 2x minus x is just x. And negative 4 plus 1 minus 3. And I get divided by x minus 1 times x minus 2 is larger than or equal to 0. Okay, so I don't even really need to do the second step, which is to factor the top and bottom completely, because it's already sort of factored for me, right? Okay, so the next step, now that I've gotten, I realize I wrote step 2 twice here. Three, 4, and 5. How about that? Okay, so I've gotten everything on one side and written it as a single fraction, and then I factored the top and bottom completely. So the next thing that I'm going to do is plot the zeros of the top and the bottom on a number line, and then I'm going to pick a test point from each interval and check whether the equality is true at each of those intervals. Okay, so we draw our number line. On here, I'm going to put basically just 1, 2, and 3, right? And I'm going to pick a test point from each of these. So I'm going to pick something like, I don't know, 1.5, 2.5, 4, and 0. Those are going to be my test points. So we try x equals 0 first. What do we get? That's going to give us negative 3 divided by negative 1 times negative 2, which would be negative 3 over 2, which is less than 0. Okay. So what does that tell us? That tells us that this whole region to the left of 1 is no good. Okay, because we were trying to get a number which is larger than or equal to 0. And we got a number which is less than 0. So the inequality is not true for x values in that region. Now we try x equals 1.5. On the top, we're going to get 1.5 minus 3. We get negative 1.5 divided by 0.5 times negative 0.5, which is going to be a negative number divided by a negative number is going to be a positive number. So this region is good. We got something which is larger than 0. Now we try 2.5. I'm just plugging into my rational expression here. I get 0.5, negative 0.5 on top. The denominator, I get 1.5 times 0.5. So I have a negative number divided by a positive number. I get something which is less than 0. So this region is no good. I have a less than 0. That's not what I want. Finally, if I try 4, well, I'm going to get 1 on top divided by 3 times 2 is going to be a number which is larger than 0. So this last region is all good. Okay. Now finally, I need to consider whether I should have open dots or closed dots on my actual zeros here. Okay. And the one thing that I said here in this, in red lettering here was that we need to be careful because the zeros of the denominator always get an open dot. So before I even worry about the other ones, let's just take care of that. We should have an open dot on the zeros of the denominator, which are just 1 and 2. So we should definitely have open dots there. I can fill in the region here in between 1 and 2, so I know that's a good region. And I can fill in the region here to the right. My question is to you guys, what should I have at x equals 3? Do we think open dot or closed dot for x equals 3? Yeah, I'm seeing a closed bracket from Abdulrahman and closed from Heidi. You're exactly right. We should use a closed dot on 3. And here's why. If you want to know whether you should have a closed dot, just try plugging it in. If we try x equals 3, what would we get? On the top, we would get 0, and on the bottom, we would get 2 times 1, which is 0 divided by 2 times 1 is just 0, right? And I want to check, is 0 larger than or equal to 0? Yeah, it is. 0 is larger than or equal to 0. It is equal to 0, so by definition, it's larger than or equal to 0. So we get a closed dot on 3. So the closed dot on 3 is really a consequence of the fact that we had a larger than or equal to sign. That's why we got a closed dot on 3. And we just have to be careful because anything that makes the denominator 0 just gets automatically thrown out, because the left-hand side, if we were to plug in 1 or 2, the left-hand side is not even defined. So if you have a number which is not even defined, how can you say that it is larger than or equal to 0? It doesn't even make any sense. It's not even a number. So to say, something which is not even a number is larger than or equal to 0 is nonsensical. So we put an open dot around the numbers which cause that kind of really funny business to happen. Okay, so our end result would be like x is in, yes, I know. X is in 1, 2 union, and then we should have a bracket 3, infinity. Okay, so that's how we solve these rational inequalities. It's kind of the same as our polynomial inequalities. All we do is we plot the zeros, and we take a test point from each subinterval and check whether the inequality is true in that region or not. Okay? Then the only thing that we have to be careful about is we have to check whether we should have closed dots or open dots, or brackets or parentheses if you want. Okay, and when we do that with polynomials, it's really just about checking whether the sign, the inequality sign, has the or equal to part. When we have rational inequalities, then we have to check both the possibility of that sign having the or equals part, and also we need to make sure that we put an open dot on any value which is going to cause the denominator to be 0, because then our inequality doesn't even make sense, much less be true. Okay, so that is about how we do rational inequalities. Okay, I think we're going to stop there for today. So if there are any questions about any of this stuff, feel free to stay after class and we can chat a little bit. Otherwise, we're done for today. Next time, we'll talk about a new topic. And yeah, have a great day. Unless you have further questions, then feel free to open up your microphone or type in the chat. Yep, thanks, Heidi. You too. Catherine or Tommy, did either of you guys have a question? Or want to see an extra example?